Section 10 is about this sort of thing here, simple harmonic motion. You've got a mass attached to a spring, you disturb it, and it bounces back and forth. Little terminology. I'll point you at the handout in a minute. It's all written out there also, but the position where the mass would be undisturbed is called its equilibrium position. So in this case, equilibrium is right there. You get it bouncing, and the maximum distance from equilibrium is called the amplitude, which looks like it's about maybe the distance between, a little further down there. Roughly the distance between my fingers there is the amplitude. The period is the amount of time for one complete vibration, such as if I had a stopwatch in my hand, start, stop, okay? Up and down again, or start up here and go down and up again. One complete vibration. Now, I mean, springs are kind of important because they are in many different types of mechanical devices, but not important enough that they'd be worth putting a whole chapter into a physics book about this sort of thing, just strictly for the sake of talking about springs themselves. The main significance of what you're looking at here is that it serves as a model for any kind of vibrational motion. If I stand here talking, okay, well, my voice makes a more complicated pattern, but if I whistle, for example, the way it makes the air molecules vibrate as the sound passes is pretty much the same thing you're looking at here, just a lot more rapid and with a smaller amplitude. If you want to talk about the motion of the electrons inside of a wire, when there's an alternating current in that wire, it's this, okay? If you want to talk about how the molecules in a solid vibrate because of their thermal motion, you know, the higher the temperature, the harder they shake, and they're like this, again, with a much higher frequency. But this general type of motion occurs in many different settings. And so the main reason for talking about this is as a model for all of those sorts of things that will come up repeatedly as you study the physical world. So over here to the handout. And even though what I was just showing you is a mass that's vibrating vertically, because that's the simplest thing to set up, let's talk about a mass that's vibrating horizontally, like one of our air tracks, which actually there's a whole room full of them that just happened to be set up there for another experiment. But say we took one of the air tracks. Oh no, I messed up the focus. I'm sorry, I didn't mean it. Okay. You have a glider on an air track attached to one end of the air track by a spring. And the reason for doing it horizontally is it takes gravity out of the equation. It turns out that if you have the spring hanging vertically, like the one I was just showing you, all it does is shift the equilibrium position over from where it would be in a weightless situation, and it'll vibrate around that point in exactly the same way that it vibrates around this point on the horizontal surface. But it makes the math a little, not terribly, but a little more complicated when it's vertically. So let's look at the simplest case, which is where it's going back and forth on something like an air track. So here you see the mass in its equilibrium position, which, as I mentioned earlier, means you could let go of it there and it wouldn't move. It would remain at rest. If you push the mass to one side, compressing the spring, it pushes back toward equilibrium. If you pull it the other way, so the spring gets stretched out, it pulls the mass back toward equilibrium. What you get from this spring, which of course the spring just acts as an idealized model for any kind of elastic behavior. I mean, even as I stand here in this room, my weight slightly deforms the steel beams in the floor underneath me by just a microscopic amount, because I don't weigh that much, and we're talking about some I-beams here. But you know, you hang a weight on the end of a wire and it stretches the wire a little bit, not nearly as much as a spring, but you get this kind of elastic behavior in many situations. And so whether this is a spring or a rubber band or whatever it is that's getting stretched or compressed, it provides what's sometimes called a restoring force, because it tries, no matter what you do, it tries to restore the mass back to the equilibrium position. This restoring force is given by an expression called Hooke's law. Put it over here where you can. The problem with moving the camera around all the time like this, before I started recording, I spent something like 5 minutes getting all the cords untangled. Hooke's law. F is the force and X is the displacement, as illustrated on the diagram in the note packet that I was just showing you a minute ago. If you look, and maybe I should put you back at that and tangle up the cords some more. Oh, hey, it focused right away. The thing I wanted to point out is notice that the force and the displacement always have opposite directions. When you displace the mass to the left, the force is to the right. When you displace the mass to the right, the force is to the left. Okay, so this is the F and the X that are in Hooke's law. And because the directions are always opposite of each other, that's the reason for the minus sign. K is a property of the spring that describes its stiffness, usually called its spring constant. That little spring that I was showing you before, the spring constant is probably somewhere on the order of 1 Newton per meter for this thing. You start talking about the coil springs and the suspension of a car, well, actually, that's the example that's coming up in a moment, and that's in the tens of thousands of newtons per meter. So if the spring is very easy to stretch or compress, K is a small number. If it takes a lot of force to stretch it or squash it, then K is a big number. So that's what that means. Probably not a bad idea to make a comment about the use of the word law here. Hooke's law describes the behavior of an idealized spring, where the force is exactly proportional to the displacement. In the real world, and I'll get back to this before section 10 is over, in the real world, that's usually not quite true for vibrating systems. It's just usually a good approximation, or let's say it's a good approximation up to a certain point. If you take a spring and start stretching it and stretching it, you know, like, I don't know if you ever did this when you were in elementary school, but certain people I can think of would sometimes take a ballpoint pen apart and get the little spring out of there and start playing with it, you know? And maybe if you ever did that, you noticed if you stretch it too far, it doesn't go back, okay? You have passed what's called the elastic limit of that spring. And actually, if you went even further, like if you started hanging 20 pounds from that little spring or something, you would go, the next step is you break it. So Hooke's law is a decent approximation to reality as long as you don't stretch the thing too far and pass that elastic limit. So it is not some basic fundamental law of nature like Newton's second law. Rather, it's a model for elastic behavior that works fairly well a lot of the time. The use of the word law is a matter of what was fashionable at the time. Robert Hooke was a contemporary of Isaac Newton. So we're talking late 1600s here. And the outlook people in that time period had was they were going around and discovering all these fundamental laws of nature. Well, for a comparison, there is the theory of relativity. The theory of relativity is now over 100 years old. And in that century, it has been put to many very stringent experimental tests. The most notable recent one being the detection of the gravitational waves that were predicted by it almost 100 years ago. And it has passed every experimental test with flying colors. Okay, it's one of the most successful models ever devised by people, but it's called a theory because that's the terminology that was fashionable in the 20th century. Hooke's law is a law because that was the terminology that was fashionable in the 17th century. Okay, so anyhow, F equals kx. We have a sample problem to illustrate Hooke's law. That's a little further down the page. And yes, I do know how the screen share function in Zoom works. It's just so much easier to do it this way. Section 10, problem 1. So when you put your weight in newtons, it makes you sound so heavy. I mean, 160 or 600 newtons is only something like 140 or 145 pounds or something. This is not a particularly, I mean, if I was that weight, I'd probably be anorexic, but 600 newtons, it sounds, anyhow. This person gets in the car and it makes the car go down. You may or may not, when that's the most noticeable is when in the wintertime, when there's like a snowbank along the curb there, you know, where the plows have pushed it back and you get in on the passenger side and the car goes down and then the door kind of plows through the snow when you're closing it because it's lower now than when you got in. So let's say this person makes the car go down by 1 centimeter. Which is probably a fairly reasonable estimate. So what does that make? Not the spring constant for one of the springs, but for the entire system, the springs on all 4 wheels. What's the overall spring constant for the, the total system. And that doesn't take long. It's just throwing numbers at Hooke's law. Sometimes I'll say F equals KX, and a student will go, wait a minute, what happened to the minus sign? Well, what happened to the minus sign is I don't care about the directions, okay? I just want to know how big the spring constant is. And so I'm going to slap absolute value signs on there. As I explained earlier, the minus sign is there to make the directions work properly. The force is in one direction, the displacement's in the other direction. I just want to throw numbers at this thing and get a value for K. So that's what happened to the minus sign. You put absolute value signs on there and it becomes F equals, the magnitude of F equals K times the magnitude of X, if you're going to go to the trouble of saying it that way. I suppose one other nitpicky point that I could make is that the weight of the person, the 600 newtons, is not exactly the force, it's the change in the force. Those springs are already quite significantly compressed from the weight of the car, okay? When the person gets in the car, that puts some additional load on the springs, causing them to compress by some additional amount. So it follows from F equals Kx that any change in the force would equal K times the change in the length of the springs. So having said all of my nitpicky little details now, if you want the spring constant to come out in newtons per meter, you have to convert the centimeter into meters. So you divide both sides by 0.01 to solve for K, and K comes out 60,000 newtons per meter. This is pretty much the same idea as the first step in this week's lab. You're going to be given a little spring about that long, and you're going to do some other stuff with it afterwards, but to begin with, you need to know what its spring constant is. So you're going to hang some weight from it, kind of like the thing I showed you at the beginning of the video, and you'll measure how much the weight stretches the spring. So you know how much weight you hung on it, and you know how much the spring stretched, and you solve for the spring constant, and that's the first step in lab number 10. So I guess I don't need to point you at the handout here, but it says, for a mass on a spring, I will show how the expression, well, I'm going to start with position as a function of time. I'm going to show you how that follows from Hooke's law. So the question is, I've got, like I showed you earlier, the little mass bouncing up and down on the end of the spring. If you disturb the mass and make it start to vibrate, how does it move as time passes? What is X as a function of time? Well, maybe it's a good idea to get kind of a qualitative idea. First of all, maybe it's better to think of, here's my frictionless surface again with the mass on it, spring, and let's say equilibrium is right there. So if you push the thing to one side, and then you let go of it, the force from the spring pushes it toward equilibrium. So the mass starts to pick up speed, goes faster and faster until it reaches equilibrium. And at that point, the force is no longer pushing on it. But just because the force is gone away doesn't mean it stops moving. It's built up a lot of momentum at this point. So it keeps on going for a while. It overshoots equilibrium. Now the spring is pulling back on it against the direction of motion, which makes it slow down. But by the time the spring stops it, it's just as far to the other side of equilibrium as where it was when you released it. Well, the spring is still pulling on it, so the thing doesn't stay there. It starts going back as the spring pulls on it faster and faster until it gets to equilibrium. And then it stops gaining speed at that point. But once again, it overshoots, compressing the spring up in front of it. And it goes back and forth. And if it's truly a frictionless environment, it'll vibrate forever. Well, of course, in the real world, there's always at least a little bit of friction, but this is a good model for what's going on as long as you don't watch it for very long, okay? Long enough for friction to have an effect. Or actually, you go, like I was talking about vibrating molecules, their thermal motion, you go down to the atomic level and there isn't any friction and things really would vibrate forever. But anyhow, that's what the simple harmonic motion means. It means the frictionless case. The case where friction is present is more complicated. So I guess simple harmonic motion as opposed to complicated harmonic motion, except that isn't what they call it. They call it damped harmonic motion when friction is present. But anyhow, that's the qualitative picture. You would expect the thing to go back and forth, as you saw at the beginning of the video. To make that qualitative picture quantitative, to make it, specific and exact, well, we have to start flinging equations around. Starting maybe right around here somewhere. F equals ma, which unlike Hooke's law is a fundamental idea, or well, a little more generally, like I said at the end of the last video, F equals the derivative of the momentum with respect to time, but as long as the mass stays constant, it's the same thing. So substitutions to put into that. In the horizontal case that I drew out on the handout anyway, the only force is the Hooke's law force. The only force in the x direction. I mean, you've got the weight and the normal force in the y direction, but they cancel each other out. We're interested in the x components because that's the direction where it's accelerating. The only force in the x direction is the Hooke's law force. Recopy M. The definition of acceleration, if you go back to pretty much the first day of the course, the definition of acceleration is it's the second derivative of the displacement. It's kind of traditional to rearrange this a little bit. It just seems tidier if you collect all the constants together into one little group and do some things like that to clean it up a little bit. So What I did to get from there to there is I divided the equation through by m and then added this negative term to both sides. Okay, so a couple lines of elementary algebra gets you from there to there. This thing that I put the box around is called the system's equation of motion, which means the differential equation that governs the system's behavior. A differential equation is an equation that contains differentials, hence the name. An algebraic equation is one that you solve for a number, okay? You know, 5x plus 12 equals 3 or something like that. You solve for x, you get a number. A differential equation is one that when you solve it, you get a function. Okay, algebraic equations, you solve for a number. Differential equations, you solve for a function. Well, a function is what I'm looking for here. My question is, how does this system behave as a function of time? The answer to that's going to be a function. Now, most methods of solving differential equations are beyond the mathematical level of this course. But one is not, which is inspired guessing. It's as if you had somebody who hadn't taken algebra yet, and you had some equation, you know, 3x plus 12 equals 5. You could say, well, you know, that this person you're talking to doesn't know anything about subtracting 5 from both sides. I forget what the numbers were. Whatever, you know, subtracting this from both sides and dividing both sides by that. And this person you're trying to talk to doesn't know any of that stuff. They've never taken algebra, but they at least can do arithmetic. And you can say to them, look, if I put x equals 4, or whatever the answer is, into the equation, it makes it a true equation, right? So therefore, that's the solution. And that's what I'm going to do with this. I'm going to say, hey, let's try this function and see if it works. And if it makes it a true equation, then it's the solution to the equation. So here's the function I'm going to stick in there and see if it works. This is supposed to mean x of t. Now, I'm not multiplying here. It's not x times t. It's, you know, like in calc class when they say f of x. Same idea, different letters, okay? X is a function of time. And a cosine of omega t plus 5. So we're going to see if this function, where omega equals the square root of k over m, k is the spring constant, m is the mass, we're going to see if that is a solution by trying it out. I guess I'll be doing that here. So what I need to do, maybe I should leave it where that stuff kind of shows also. I need to take this function and figure out what its second derivative is. And then I put the derivative here, put the original function there. Does it come out being true? So let's get started on, well, the first step would be the first derivative. And then I have to take the derivative again after that. You take a derivative, oh, I should have labeled those. A and phi are constants, okay? Constants that depend on the initial conditions. Exactly how and when did you release the mass when it started to go up and down? So from a mathematical point of view, they're more or less constants of integration. So omega stands for this, and A and phi are just constants determined by how and when you release the mass. When you take a derivative, a constant just sits around and does nothing, okay? So recopy the A. And then derivative of cosine is minus sine. But it's not just the cosine of t, okay? It's the cosine of something a little more complicated than that. So you have to use the chain rule. The way I don't know how it was explained to you in calc class, or even if you've gotten quite that far yet, but the way I always think of the chain rule is that when you have a function of a function, what you get for the derivative is it's the derivative of what's outside the parentheses times the derivative of what's inside the parentheses, okay? So for the derivative of what's outside the parentheses, the derivative of cosine is negative sine. That would be sine of omega t plus phi. Times the derivative of what's inside the parentheses. Well, phi is a constant. Derivative of a constant is 0, so that's going to go away. Over here, t to the first power, its derivative is t to the 0 power, which equals 1. So omega times 1 plus 0 is the derivative of what's inside the parentheses. Well, let's clean that up a little bit before we go on. We've got a constant at the beginning. We've got another constant at the other end. Let's rewrite it where they're all kind of gathered together like this. So I don't know about you, but I think that looks better. And now differentiate again. Constants just get recopied. Omega and A are constants, so they just sit there. Derivative of sine is cosine. And once again, you need to use the chain rule. Derivative of what's outside the parentheses times the derivative of what's inside the parentheses. Outside the parentheses, the derivative of sine is cosine. Derivative of what's inside the parentheses, another factor of omega. Well, notice part of it that goes from there to there, A times the cosine of omega t plus phi. That's the function I started with in the first place. We've just kind of gone around in a circle. Except for a factor of minus omega squared. So the second derivative of x is minus omega squared times x. Let's stick that into, this is becoming too many arrows. Guess you can follow that. The second derivative then is, maybe I should write it out. For the second derivative, I've just shown that that's equal to minus omega squared x. And then for this other term, k over m, well, k over m is equal to omega squared, because that's what I said omega equals back here. So k over mx, that would be a positive omega squared x. So yay, it works. That shows that this is in fact the solution of this differential equation. And it correctly describes where that bouncing mass is at any time t. Furthermore, and I'll write this all out over here in just a moment, but along the way here, we have also obtained the velocity as a function, because that's what the derivative is. This is velocity as a function of time here. And this is acceleration as a function of time here. So we not only have x of t, but maybe I should point it back over here for a moment. Velocity is a function of time. I called this coefficient Vmax because the extreme values of the sign are plus and minus 1. Okay, the absolute value of this factor here never gets any bigger than 1, and therefore the velocity never gets any bigger than omega a times 1. And so that would be the maximum velocity, the speed that it passes through equilibrium with. Okay, the speed maxes out as it goes through the middle, where x equals 0. So that's v of t, and then acceleration, same thing. I take the thing that I had back over there for the second derivative. The coefficient of the cosine would be the maximum acceleration, A max. That coefficient is that. Little a for acceleration, capital A for amplitude. So these three equations are to simple harmonic motion. The first week of the course, we looked at uniformly accelerated motion, motion under the influence of a constant force, like a freely falling mass, for example. We had a list of equations there that I could have derived in a sort of an analogous way if I wanted to go at it in that way at that time. The equations there were acceleration equals a constant. If it's a free falling object, for example, the acceleration would equal 9.8. You had velocity equals v initial plus at, and for x, it was v initial t plus 1/2 at squared. What those three equations are for uniformly accelerated motion, these three equations are for simple harmonic motion. Position is a function of time, velocity is a function of time, acceleration is a function of time, all three of which vary sinusoidally rather than, being constant. So back over here to the clipboard. So terminology, this kind of motion is called simple harmonic motion. And what do I mean by this kind of motion? It means motion with a linear restoring force. In other words, force is directly proportional to x. Restoring forces don't have to be linear. We'll see an example of that later in this section when we look at a simple pendulum. If the restoring force is linear, in other words, if it does obey Hooke's law, then as I just showed you in painful detail, it follows from Hooke's law that position as a function of time will be, well, I had cosine over here. The picture I drew on the note packet here was sine. Whether it's sine or cosine just depends on what time you start the clock, okay? If you start the clock right there, instead of starting the clock there, then it's a cosine instead of a sine. I made some comment once about sine and cosine being basically the same function anyhow, and there was a math major sitting over here on the left-hand side of the room, and she just about flipped out when I said that. So, no, sine and cosine are not the same function, but you know what I mean. If you just take it and slide it over, a sine becomes a cosine. Anyhow, if the restoring force is not linear, well, you may very well still have periodic motion, some pattern that repeats itself over and over again. but you'll get some repeating function that is not sinusoidal. It's not, you know, sine or cosine or some phase shifted version of that. Could be something like this. The same pattern from there to there repeats again and again and again. It's a type of vibration, but it's not harmonic motion. So that's what that word means. Harmonic, a synonym would be linear, harmonic, linear, you know, linear restoring force. Terminology that goes along with talking. I already mentioned briefly some of this right at the beginning, but amplitude and period and all that sort of thing. Let's point it at the blackboard again. So what I'm going to do as soon as I erase this is I'm going to draw a graph of this function. The one for x as a function of time, so that on that graph I can point out what some of this terminology means. Maybe actually, no, I should have done, I should have drawn the x-axis afterwards. I like the way it looks a little better if I put it maybe about there. So, first of all, capital A for amplitude. The peaks line up with x equals plus A. The troughs line up with x equals minus A. A stands for amplitude, which can be defined as the maximum displacement, the maximum value of x. A mistake I see occasionally is peak to valley is not the amplitude. Peak to valley is twice the amplitude. The amplitude means from the center line to either extreme. And then there's this, so that's the one constant that I hadn't quite explained yet. The other one, phi, that right there, that particular value on the horizontal axis would be minus phi over omega. A depends on how far you pulled the mass from equilibrium before you let go of it. The farther you pull it, the bigger the amplitude. The phase angle depends on when you start the clock. Different values for the phase angle would take this curve and shift it horizontally one way or another along the x-axis. Now, when you're just some guy standing in front of a chalkboard making up examples, you can get rid of the phase angle by just saying, oh, well, let's agree that we will start the clock exactly when the curve is peaking out, because It's going to be easier if we have fewer numbers to drag around. That's really easy to say when you're just standing in front of a chalkboard and making stuff up. But for example, when you go to do the lab for this section, you'll have a mass bouncing up and down like the one you saw at the beginning of this video, and you've got one of the motion sensors that you've used before, for example, in the air track labs. You're going to record its position as a function of time using that motion sensor hooked up to a computer. Well, nobody's reactions are quick enough to click record exactly when the thing peaks out, okay? So you're going to have a non-zero phase angle in the data for your, well, at least almost everybody, you know, 50 different people do the lab, probably one of them will, just out of good luck, click it at exactly the right moment that their phase angle is pretty much zero. But in the real world, you quite often need that. But here in the not quite so real world, I can get rid of that by just saying, we'll agree to start the clock at the appropriate time. That gets rid of that. So the phase angle equals 0 if the clock starts when x equals capital A. It's all the way out to its full amplitude. Next thing on the list is the period. Period, once again, means the amount of time it takes to go through one complete vibration. Time for one complete vibration. To get an expression for that, a formula, let's look at that graph again. And actually, this doesn't have to be position as a function of time. It could be velocity as a function of time or acceleration as a function of time. They all have the same period. Whichever one it is, let's say that this peak right here is where just a second. No, you were supposed to pause. Okay, I'm back. So here's our graph. Y equals a cosine of omega times the time plus the phase angle. Let's consider one complete cycle, okay? And, you know, it doesn't matter what the phase angle is. Whatever point in the cycle the curve was at here, you've completed one period when you get back to that same point in the cycle. Well, the thing to notice is that between here and here, the value of omega t, you know, the rest of the thing stays the same, but omega t goes from 0 over here to omega times the period, okay? When you've completed one cycle, that's what one period means. Well, that's where the graph has gotten to 2 pi radians. So that means that omega t is equal to 2 pi. Now, if you flip back a little bit in your notes, it's sort of erased up here on the blackboard at this point, but omega means the square root of k over m. So I'll fill that in. So if I do a little algebra and solve that for t, kind of squeeze that in on the bottom here. I guess I need to lower the camera a little bit if you're going to see that. Divide both sides by the square root of k, multiply both sides by the square root of m, and that solves it for the period. So the amount of time that it takes this thing to go back and forth once depends on the mass and the spring constant, which, you know, if you want to look at it from a conceptual point of view, instead of all these equations and graphs and everything, more mass means more time because mass is inertia, okay? If you've got something heavier on the end of the spring, it's harder to get it moving in the first place. Once it's moving, it's harder to slow it down again. So the inertia slows down the vibration. More mass means more time per cycle. You've got an inverse relationship. I mean, it's not exactly an inverse proportion because there's a square root in there, but it's still an inverse type of relationship between the period and the spring constant. A bigger spring constant means a spring that pulls harder. So it's going to get the mass going quicker because it's pulling harder. And you know, the other stages in the process after that also take place quicker. After it passes equilibrium, it'll stop it and turn it around quicker, and so on. So more stiffness means bigger forces, which make it go faster. Bigger spring constant, less time per cycle. So that's kind of the physical meaning behind the equation. You do want to try and avoid having this be a course that just involves throwing numbers at equations you don't understand. And people are sitting out there going, he's on to us. Next thing on the list is the frequency. I've got to put it back up a little bit. The frequency tells you the same thing as the period, just in a different way. Once again, we are recycling a letter from the very recent past. In Hooke's law, capital F means force. Here, lowercase f for frequency. So don't get those mixed up with each other. Frequency means the number of vibrations, well, more generally, the number of vibrations per unit time. The time would typically be measured in seconds. So the period tells you the number of seconds per cycle. The frequency is the number of cycles per second. Well, seconds per cycle, cycles per second. By definition, these things are reciprocals of each other. And I'd have to pull out the formula sheet to be completely sure, but I'm about 99.5% sure that's one of those relationships that is not on the formula sheet. Rather, it says at the beginning of the section, you should know it. If you don't know that these things are reciprocals of each other, you probably don't understand what they mean in the first place. This would be the general definition. Frequency for any kind of vibrating. A synonymous word is oscillating. Just be careful of that one. I've heard people use the word, mispronounce it slightly, and call it osculating instead of oscillating. It's kind of an obscure word, but I've been told the word to osculate means to kiss. And maybe just better to stick with the word vibration. Anyhow, no matter what kind of vibration it is, harmonic or not, this is what the word frequency means. So this would be true in general. If it is a harmonic oscillator, then, well, it's been erased now, but if you go back a page or two in your notes, there was, oh wait, no, it's still over there. That's the thing down in the corner. This thing over here, T equals 2 pi square root of m over k. If you want a formula for the frequency of a harmonic oscillator, the frequency is just this turned upside down, okay? Frequency is the reciprocal of the period. The period is equal to that. And so unit to measure it in. Well, by definition, it would be the number of cycles per second. And if you want to go back like about 50 or 60 years, people used to just abbreviate it CPS for cycles per second, but pretty much anybody alive today calls that a hertz. Named after Heinrich Hertz, the guy that discovered radio waves about 150 years ago. Notice, remember that back in the beginning when I first launched into all of this, I said, let's see if this trial solution works in the equation of motion, x equals blah, 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 where omega equals the square root of k over m. Well, I'm just about to the point now where we can see the physical significance of that square root of k over m thing. If I take this and multiply both sides by 2 pi, I multiply both sides by 2 pi, I've got that 2 pi f equals the square root of k over m. But I said back at the beginning that the square root of k over m was this collection of numbers that I was going to call omega. So omega is actually the frequency measured in radians per second. Now, see, 2 pi radians per revolution, or 2 pi radians per cycle, either way you want to say it. See, there's sort of a connection between harmonic motion and uniform circular motion. Imagine I had someplace to write. Got a clock. And maybe you've taken the glass off of the front so you can get in there. And you put a wad of chewing gum on we were walking through the grocery store the other day. Of course, we had our masks on. And my wife goes, oh, I stopped myself at the last. She was chewing some bubble gum and she was just about to blow a bubble inside of her mask, which would not have gone well at all. But anyhow, imagine you put a blob of chewing gum on the end of the second hand. Now, if this is a clock where the second hand sweeps around nice and steady instead of the kind where it goes jerk, jerk, jerk every second. If you imagine this thing in a nice, smooth, uniform circular motion. Well, if I'm looking at the clock face on like this, I see uniform circular motion with an angular velocity omega, 1 revolution per minute for its angular velocity, except, well, you could do it in revolutions per minute, you could do it in radians per second. But if I am over here, looking at the clock from the side, what I see is the piece of chewing gum going down and up and down and up, and that's simple harmonic motion, okay? Except I was standing over here where you couldn't see me waving my finger around. Okay, repeat. I'm over here looking at the side of the clock. Down and up, down and up, down and up. Look at it face on, simple or uniform circular motion. So if you're looking at it this way, omega is the angular velocity. If you look at it from over here, it's the so-called angular frequency. That's why they use the same letter, omega. So this thing omega is the name they give it is they call it the angular frequency. In other words, it's the frequency in radians per second, and I already explained a few weeks ago that a radian isn't a real unit. Radians per second is actually just seconds to the -1 power. So basically, this is the only place in the entire physics book that I can think of where they use 2 different letters for what amounts to the same thing. Which letter you use depends on what unit it's measured in. Anything else, like, if you're going to calculate gravitational potential energy, what is mgh for this eraser? Well, I call the height h if I measure it in feet, and I call the height h if I measure it in meters, okay? But for some reason, with frequency, they use the letter f if it's measured in cycles per second, but they use the letter omega if it's measured in radians per second. 2 pi radians per revolution. So that's what's going on with this. So omega, frequency in radians per second, f, frequency in cycles per second. So that's all the introductory stuff. I like to break these, instead of having a 3-hour lecture, I like to break these into 2 recordings at least per unit. So I think this is where I'll put the break, and whether you come back in 5 minutes or whether you come back, 2 days from now, we'll do the other half of, I'm going to come back in a couple minutes. I'll still be wearing the same shirt, but we'll see you on the other side.